I wanted to start the unit on chemical equilibrium with a little bit of review of some of the basic concepts. Hopefully you've heard of chemical equilibrium before. Essentially, in order for you to have chemical equilibrium, first of all, you need to have a reversible reaction. All right, and the way that you generally represent a reversible reaction is you have two parallel arrows, one going to the right, one going to the left. All right, so when you do this, when you have a reversible reaction, you actually have two reaction rate constants. All right, so if we just got rid of this bottom arrow right here, we could say A going to B. All right, that process would have a reaction rate constant. All right, which we could represent as Kf. All right, the rate constant for going from B to A, the reverse process, we can call that Kr. All right, one thing that you'll commonly see when you see reversible reactions represented is that the forward rate constant will be given some number and the reverse rate will be given the negative number. For example, this might be K with a 1 subscript, where the reverse would be K with a negative 1 subscript. All right, and that's just a common convention that they use when doing the reaction rates of reversible reactions. When you have what defines an equilibrium? An equilibrium is the state where you've got a reversible reaction where the forward rate equals the reverse rate. All right. So one thing to clear up: equilibrium is not the point where the reaction stops. All right. So you get to a situation where the concentrations of the reactants and the concentrations of the products stay the same, but that's not because no reaction is occurring. It happens because the forward rate equals the reverse rate, and if the forward rate equals the reverse rate, the concentrations are going to stay the same. All right. So if we had this reversible rate, we could represent the forward rate as the following. All right. It would be Kf times the concentration of A, and the reverse rate is Kr times the concentration of B. One thing I want to point out is that when you're talking about a rate constant, the K should be a lowercase k. All right, and I'm going to do that in contrast to an equilibrium constant, which is going to be an uppercase K. All right, so at this state of equilibrium, remember that's the state where the forward and reverse rates equal each other, we could take this expression and we could rearrange it to this right here. And what happens is you would have a constant divided by a constant, and a constant divided by a constant is just going to be another constant, and that constant is going to be the KEQ. All right, so you can put equals KEQ out here. All right, so and so notice that when we do that rearrangement, that puts the thing that would be on the right in the numerator and the things that are on the left in the denominator. All right. So one thing I want to mention is that a lot of times when you see reactions, if this were an irreversible reaction, all right, and by irreversible, I would mean you would only have an arrow to the right, all right, no possibility of the thing on this side going back the other way, all right. If you have that situation, we generally call the thing at the base of the arrow reactants and the thing at the point of the arrow products. All right, but notice that when you have a reversible reaction, this thing can go either way. All right, so what ends up happening is that the terms reactants and products kind of become somewhat arbitrary. All right, it's kind of like saying water or ice. If one of these is water and one of these is ice, what's the reactant and what's the product? All right, well, it depends on what's happening. If something is freezing, then water is the reactant. If something is thawing, then ice is the reactant. So because this can be a little bit confusing, we still, for the sake of simplicity, still use the terms reactant and product. But generally what reactants mean is just going to be whatever's on the left. All right. So even though this is reversible and it can go either way, generally we're going to refer to the stuff on the left as a reactant and the stuff on the right as a product. All right. You just need to realize that technically either could be reactant or product. All right. And it's just we need some language to describe the things in this reaction. But since in a reversible reaction, either could be reactant or either could be product, technically we could have drawn this reversible reaction like this, all right? Because there's no starting material, no ending material. It's just relative to how you draw it, all right? Well, if we define our equilibrium constants as the stuff on the right divided by the stuff on the left, well, the way the constant that we end up getting could be very different depending on the way that we write this. All right. So one thing that's important to remember is whatever your KEQ is that you report is always relative to the way the reaction is drawn. All right. So if I were to say just say the interaction between A and B, what's the KEQ? You couldn't say that because I wouldn't know whether you were saying this interconversion between A and B or this interconversion of A and B, all right? And depending on how you write this, it would totally change the way you would express the KEQ, all right? So notice the relationship between these two forms is that they are reciprocals. And so the thing to remember is that every time you report a KEQ, you have to see a written down equation that shows it, because that defines what's on the left and what's on the right, and we need to see that so that we would know what this means. So what does the equilibrium constant mean? All right. So notice that you always have the products on. You notice I use the term products, but really what I mean is what's on the right hand side. So from here on out, when I say products, just remember that means what's on the right side. Okay. You have the products raised to whatever the coefficient is there as the exponent, and you have the reactants raised to their coefficients there. So notice what this means. Let's think about if we had a large KEQ. All right, what would happen? How would you get a large KEQ? Well, that would occur from a situation where you had lots of C and very little of these guys down here. All right, so you'd have mostly this, not a whole lot of that. All right, so the opposite of that is what would it mean if we had a very small KEQ? All right, that would result from the situation with a small numerator and a large denominator. So you would have very little of this and a lot of this right here. So essentially, whenever you have a very large KEQ, all right, essentially that's going to mean a reaction that seems to have, quote, gone to completion. All right, so because you'd have mostly this. All right, so to have mostly this, it would mean most of this has been converted into this, so that you don't have much of this anymore and you have lots of that. All right, alternatively, if you had a very small KEQ, that's not a lot of this and mostly this, well, what would happen if you just took some A and B and you mixed them together and nothing really happened? They didn't really react that much. All right, well, that would mean you'd have lots of this stuff swimming around in solution, and you wouldn't have any of this right here, or very little of this. All right, and that's indicative of something with a very small KEQ. So you'd say that that's something, a small KEQ is a reaction that hardly proceeds. All right. So one thing about the units of a KEQ. All right. So even though you could look at this and say, well, this is these concentrations are all in molar. All right. You could have a molar squared. This would be molar squared, and you'd have a molar here. So we'd still, if we counted out all of our units, we would still have a molar in the denominator. All right. But the thing is, you should realize that different reactions have different coefficients. All right. And so because of that, if we were to include the units in the KEQ, depending on the reaction, the KEQ would have different units. All right. So for example, if this right here were to be 3C, all right, that would change this exponent here, and it would change the units that would be in KEQ. All right. And so because different reactions would have different units, the convention, which is just the normal way of doing this, is to just not write the units for KEQ. All right. So yes, I understand that these things would have units in what we're putting in, but when we write the KEQ as an answer, we just give it without units. So while writing these KEQ expressions might seem fairly straightforward if you've got a balanced reaction, there's one thing to remember when writing these, is that not just any chemical species can be part of the equilibrium expression. All right. So what that means is if I give you a reaction right here, just because it exists in this reaction doesn't mean that it necessarily would go into the expression. All right. So what's the situation for where it would and where it wouldn't? Okay. And before I go on much further, notice I use the term chemical species here. And the reason for that is this could refer to something that's either a product or a reactant. All right. So for these guys right here, so instead of keeping on saying, product or reactant, I'm just going to say species, all right, which means it could be either a product or a reactant. All right, so essentially when doing this, in order to be part of this equilibrium expression, that chemical species has to be something that has the potential to have a variable concentration. All right, so what I mean by that, so first of all, examples of materials that can have variable concentrations. There's two major categories, gases and solute particles. All right, so in contrast to that, things that can't have variable concentrations are solids or neat, and neat means just pure liquid. All right, and I'll give you an example of that in just a second. All right, so first of all, things that can have variable concentrations. Let's pretend that these two, that you've just got a box, and in this box I've got 3 gas particles in this box right here, which is the exact same volume as this box right here. I just have a lot more gas volumes. All right. So one thing that we know about gas particles is you can put, like, they can have the space between them reduced so that you can fit a lot more in the same amount of space. So is there a certain number of moles in this area right here? Yes. And is it, can you divide that by the volume? So that would be that would correspond to the concentration here. So notice in the same volume you can have different amounts of moles of a gas. All right. Same thing with solute particles. All right, I can have a dilute solution or I can have a concentrated solution. All right, so I can have different amounts or variable amounts of solute particles in that same volume. All right, so by contrast, let's pretend that we have a pure solid, like this is a cube of sugar. All right, so pure sucrose. All right, so the thing about a pure solid is that for a given volume of that solid, so let's pretend we're talking about a sugar cube, or something, and we're talking about the exact volume of that sugar cube. Well, that sugar cube is always going to have the same number of moles of sugar. All right, it's not like I have two apparently identical sugar cubes and I say that one of them's got twice as many molecules as the other. All right, if they're the same size sugar cubes, they're going to have the same number of moles of sugar in them, right? Because it's the same number of molecules in sugar. All right, it's not the same like the situation here where the same volume can have different amounts. All right, so same thing with the pure liquid. If this was 1 milliliter of a pure liquid, like let's say for example, a milliliter of gasoline. All right, well, gasoline is not a solution. It is a pure liquid. All right, it's not like you can have a gallon of dilute gasoline or a gallon of concentrated gasoline. You just have a gallon of pure gasoline. All right, so and what happens in these types of materials is that ratio between the number of moles versus divided by the volume that much material occupies is always going to be the same. So if I had a large sugar cube versus a small sugar cube, the number of moles in the small sugar cube divided by its volume is going to be the same ratio as the number of moles in the large sugar cube divided by its volume. All right. So essentially what it means is that the concentration, it's kind of meaningless to talk about the concentration of these types of things in the same way that we would of these types of materials here. So what that means is that whenever you would never talk about the concentration of an undissolved solid or an undissolved liquid. All right. So this is going to have an effect on the way that we write things. So if we had this expression right here, all right, notice that these two things are solids. All right, so if we were to write this the normal way, we would take the stuff on the right, put it up top, put this on the bottom. But notice that since these two things are solids, we do not include them in a rate expression. All right, so the KEQ would just be equal to this right here. Luckily, most of the things are just gases and solutions.